Okay, so now we look at the final result of this section, namely that theorem we were discussing about. It is due to Riemann. So in this theorem we have a series of real numbers that is conditionally convergent but not absolutely convergent, and let L be any real number whatsoever. Then the theorem states that we can rearrange this series so that the rearranged series converges to L. That is, there exists some bijection on the set of natural numbers such that using that bijection f, if you rearrange the series, which will look like this, of course, you rearrange the subscript values, this series will converge to L. So this theorem is obviously peculiar because no matter what your choice of L is, there exists a rearrangement so that the resulting series converges to L. In other words, the series can be rearranged to converge to any real number. So let us now see how we can prove this. Now the proof that is given in the text is incomplete. Incomplete means it has gaps which were left intentionally for us to fill in one of the exercises. So here also we are going to proceed like that, and we will fill in the gaps later. So let's see. So the proof starts off by considering those two sets, A plus and A minus, that we came across in the previous lemma. So this is how it starts. Let A plus and A minus be the sets from the previous lemma, that is lemma 8 to 7, be the sets in lemma 8 to 7, i.e. let's once again see what the sets were, and in fact let me write it in the line below. A plus is the set of those indices for which the corresponding terms in the series are non-negative real numbers. That is, A plus consists of those n's for which an is non-negative, and A minus consists of those n for which an is negative. Now we already know from the previous lemma that the sums of these terms an over A plus and A minus are both divergent sums. We know from lemma 8 to 7 that the sums summation of an as n varies over A plus and summation of an as n varies over A minus are both divergent. Okay, this we have already seen in the previous lemma. And because of this, and in fact we actually already know, in the course of proving this lemma, we also saw that A plus and A minus are infinite sets. In particular, the sets A plus and A minus are infinite. Now we proved, while proving this lemma, that A plus and A minus are actually infinite from what was given in the hypothesis of the lemma. If the hypothesis was the same that we have here, that is, our series is conditionally convergent but not absolutely convergent. But then we went on to prove that this and this are divergent. Here, however, the way the author is writing this part, it seems like this part is a consequence of the previous part. Previous part means this part. The fact that these two series, these two sums are divergent implies in particular that these two sets are infinite. And yes, it has to be, because if this is finite, say, then this is always convergent. In a finite sum, there is no question of divergence. So anyway, the fact now is that A plus and A minus are infinite. But they are not just any infinite sets, they are infinite subsets of the set of natural numbers. And we already know that for such sets, we can find increasing bijections of such a set with the set of natural numbers itself. And that fact is our this proposition 815. By proposition 815, there exist increasing bijections F plus from n into A plus and F minus from n into A minus. This one, and F minus from n into A minus. These are bijections, and not just any bijections, they are increasing functions, in the sense that if you consider two natural numbers such that n is less than m, then f plus of n will be less than f plus of m. This is what it means for f plus to be increasing. Similarly, increasing nature of f minus means having this also. Okay, so such functions exist, and that fact is coming from proposition 815. Okay, so now what we are going to do, we are now going to define a sequence of natural numbers recursively in a specific way. Let's see how that thing goes. So all these things that we see here, they are consequences of the previous lemma, and the consequences of the fact that we are considering the sets A plus and A minus. That's it. We haven't done anything here new. We haven't done anything new here. We are just writing the consequences. Now we are going to do something. Now we are going to do, oh, but before, okay, this part is not over yet. You see, these are sums, right? Sums over some infinite set. Now because we know that a plus and a minus are both infinite, so they are both countable, and as a result these sums can both be turned into ordinary infinite series, provided we have to consider some bijection between the set over which the sum is being considered and the set of natural numbers. Now what does divergence of these two sums mean? It means then the series summation a of f plus of m and the series summation a f minus of m are both divergent. But why? You see, if it turns out that for such a bijection this ordinary infinite series is convergent, then by the definition of absolute convergence this sum would be absolutely convergent, and absolute convergence implies ordinary convergence. So that would then imply that this sum is convergent, which however is not true, because this is divergent, this is also divergent. So that means no such bijection exists for which this series will be convergent. For every bijection this will be divergent, like that this will also be divergent. In particular, for these two particular bijections also these two series are going to be divergent. Okay. So now we are going to do what I was saying there back then. We now define in the next paragraph a sequence Ni of natural numbers recursively as follows. Okay, so now I am going to give the recursive definition of this sequence. A sequence of natural numbers means each Ni is a natural number. Suppose that J is a natural number. J is any natural number, or J is just some natural number. Suppose that J is a and that Ni has already been defined for all natural numbers I less than j. Okay, and something else about the starting point of this recursive definition is this. This is vacuously true. Is that how the author is writing? This is yes, this is vacuously true. If, or we should not write if but when, because j will take the value 0 also when j is equal to 0. We then define the next term in the sequence nj as follows. Okay, let us now see how nj can be defined. There are two cases that we have to consider. Case 1, if it turns out that this finite sum ani, where I starts from 0 and it stops short of reaching j, it just goes as far as it can go, but it does not reach j. If it turns out that this sum is less than L, if you want, you can consider the greater than or equal to L in this case 1 also. It does not matter, because we anyway have to consider the two cases. One is where this type of sum is less than L, and the other where it is greater than or equal to L. So let us consider the less than L here. Then we define nj to be equal to the minimum of this set, not equal to ni for all I less than j. On the other hand, if that's not quite what we have here. It's not n. If this is less than L, then this n should come from a plus. Otherwise, what is the use of the sets a plus and a minus? On the other hand, if summation ani, where I varies like this, turns out to be greater than or equal to L, then we define okay, let me keep this part for now. Then nj is defined to be equal to, again, the minimum of this set instead now, a minus, such that n is not equal to ni for all I less than j. Okay, the definition looks quite complicated, no doubt about that. Okay, at first glance it looks quite complicated. But let us try to see what the definition means actually. So what the author is saying is that suppose that j is a natural number, any natural number, and suppose that the terms in our sequence that we are trying to define, that is this sequence, the terms which have lower suffix values than nj, that means their subscript values are less than j, they have already been defined. That is, all the ni's for I less than j already we have defined in some way. Then we are going to define nj in this way. Also, the author is mentioning this is vacuously true when j is equal to 0. This part may sound a little confusing, but we will understand everything. Okay. So let us first of all try to recall what is it that we do when we define something recursively. Recursive definition demands what? And because here we are defining a sequence of natural numbers itself, what is it that we need to do to have a recursive definition? The first thing we need to do is we need to say what n0 is actually. That is the first thing. And then if j is a natural number, and suppose all the ni's already have been defined for all I less than j, then nj next has to be defined in terms of those already defined ni's in a unique manner. That is, all those ni's by some rule are going to give us nj, and that nj should be unique, some unique natural number. If this happens to be true for all natural numbers j, then the principle of recursive definition guarantees that this sequence is uniquely defined and determined. Is that happening here? Let's see. It seems that the beginning itself is a little confusing. This is vacuously true when j is equal to 0. So now our first thing, the first aim is to see what n0 is in this case. So let's see that first. Okay. So we are of course going to use only what we have here. That's it. In order to define n0, we have to look at this series, this sum, finite series or finite sum. Let us write this when j is 0. In that case, the sum is this. Okay, but you can immediately see that in this sum actually there is no I, or rather I should say that I actually does not take any value, because no I can satisfy these inequalities simultaneously. So you can think of this sum as a sum over a set over which I is varying, where that set is empty set. In other words, this sum is actually equal to this. And in fact, if you go back to the definition of finite sums, there itself you will see that the values of such sums have been defined to be equal to 0. This sum also has value 0. Well, if you find the fact that this is equal to this somewhat confusing, you do not need to think of this at all. You go back to the definition of finite sums, there you will see that in that definition, this sum has been defined to have the value 0. Okay, so we know what this series is in order to determine what n naught now is going to be. So this value is 0, irrespective of what a n I actually may be. Okay. Now L is also our choice. L was any real number in the statement of the theorem. So there are of course going to be two cases. This may be less than L or this may be greater than or equal to L. If this is less than L, then according to definition n naught should be the minimum of this set. N is not equal to ni for all I less than 0. But you look at this set carefully. Do you see that this set is going to be actually equal to the entire set A plus? Why? Let us see why. So what I am saying is that this is equal to A plus. There is no doubt that this is a subset of A plus. From the definition we can see that immediately. But if you take any element of A plus, say n belongs to A plus. Now what do we need for this n to be an element in this set? This condition should be true. What is this condition? This n is not equal to ni for all I less than 0. But for all I means for all natural numbers I less than 0. Of course, there is no such natural number. If you find this a little confusing, you can always rewrite such a statement in this way as an implication. That is, if your I is a natural number and I is less than 0, then n should be not equal to ni. This is the same as this condition. Is this true? Is this true? Yes, it is true. Why? Because it's an implication which has a hypothesis and which has a conclusion, and the hypothesis is false. Because there is no natural number that is less than 0. So the implication is vacuously true, but true nonetheless. So that is why any n belonging to A plus also satisfies this condition, and hence any such n is also an element here. And that's why, just like this set is a subset of A plus is also a subset of this. That is, they are equal. So that means this is nothing but the minimum of the set A plus itself. N naught is the minimum of the set A plus. Now the next question is, does this minimum exist? What is the guarantee that the set A plus has a minimum? You see, we already know that A plus is a subset of the set of natural numbers, and it is also infinite. So it's obviously non-empty. And every non-empty subset of the set of natural numbers has a minimum element. That is the well-ordering principle, which we proved. We all have already proved that somewhere. I don't exactly remember, but we have proved it somewhere. So the minimum exists, and the minimum of A plus, of course, is a fixed, concrete, natural number. Depending on A plus, of course, but A plus itself is fixed, so this is unique. So n naught is being determined uniquely in this situation. But keep in mind, all of these things happen if 0 is less than L. But if 0 is greater than or equal to L, that is if this sum is greater than or equal to L, then by the condition 2, n naught in that case will be similarly the minimum of A minus. But just like A plus, A minus also is a non-empty subset of the natural numbers, in fact an infinite subset. So this minimum is also uniquely determined. So we get the fact that the first term of our sequence is uniquely determined by these conditions. That is the first condition for a recursive definition. But what about the other subsequent terms? The other subsequent terms, say you have, now assume that j is in fact some positive natural number, and so that there are i's less than j. Actually there are i's less than j that are natural number, and say the n i's have already been defined. Now you need to say that nj is also a uniquely determined natural number. Do these conditions guarantee that? Let's see. So now there is no special value of j. J is just j. Exactly one of these two things will happen. Say this is true. Say the sum of, the value of this sum is less than L. Then according to definition, nj is the minimum of this. Okay. Now you look at this set. What is this set? This set is A plus, let me write it here itself, so that n naught has been understood. So now we are going to understand general nj. This set actually is simply just this. That is because it's the set of all those elements in A plus that are different from the previous n i's. So from the set A plus we are removing these natural numbers, and that's what this set is. The resultant is the set. Now because we know that A plus is infinite, so it does not matter how many n i's we are removing, that number is always finite. So it does not matter how large j is, and as a result how large a finite subset we are removing from A plus, we will still be left with a non-empty set, this entire thing. This is still a non-empty set, and of course it's still a subset of the set of natural numbers, and as a result it will have a unique minimum, and that minimum is nj. So in this case also nj is uniquely determined. And if instead of this condition is true, same thing. Now instead of A plus you will be having the set A minus, which is also infinite, due to which this minimum is also similarly uniquely determined. So we see that the recursive definition actually works, and it gives us a unique sequence of natural numbers defined recursively in this way. Okay. And all of these things are going to be expressed in this next few lines by the author like this. Note that this is what Tao writes. Note that this recursive definition is well defined. Okay, well defined for what? Because because of these things, of course, a plus and a minus are infinite. Because a plus and a minus are infinite. And so those sets, this one and this one, are non-empty. And so the sets not equal to Ni for all I less than j and for all I less than j are never empty. Okay, so now we have a sequence of natural numbers, but what are we going to do with this sequence? Now next comes a list of claims which will take us towards the final conclusion of this theorem in steps. And in proving these claims, the author has not done it actually. Most of what now are going to be written, these things have been left to us. So simply it has just been mentioned that the following claims can be verified. One can then verify the following claims, and these are the claims given as bullet points. The function which maps every natural number j to the sequence element nj, that mapping is injected. That mapping means this is just the sequence itself being written as a mapping. The function is injective. That means it's one-to-one. And the author asks why. We have to answer why in the exercises. Then the next bullet point is this. Case 1 occurs infinitely many times, and case 2 also occurs infinitely many times. Again, why? We have to next prove this, and something is else is also said here. Prove by contradiction. Okay. Next, there are other claims as well. The next one is about surjectivity. The map is surjective. That means it's onto again y. Then there are two more claims. The next one is about the limit of these terms a and j. We have the limit of a and j as j increases indefinitely equal to 0. Again y. Something else is there that we already know, not from corollary, what 7 to 6, that this limit is already there. This is something we already know. But why is this also 0? And finally, we have limit of, shall I be able to write it here? Do I have space? Let me write the sum first. A(n)(i) less than j, limit j approaching infinity. This looks very bad. A(n)(i) is actually equal to L, and that's it. These are the claims, and the final claim means what we are claiming in this theorem. That claim now follows by just setting f of I equal to Ni. By setting or taking to be Ni. Okay, let us now try to see these y's. Of course, we are not going to answer now. We are going to do it when we solve that exercise. Okay. Instead, let us now try to understand what these claims mean. What they mean, I mean, as sentences that we already can see, we can see that here. That is simple. There is nothing else about that. But what are the claims saying? Note that the first claim tells us that this function is injective, and the third one tells us that it is surjective. So if we define this function f in this way, then this f is going to be a bijective function, a bijection from the set of natural numbers to itself. And it is in fact this bijection that the statement claims is there, which can be used to rearrange the terms of the series so that the rearranged series converges to L. But there are other things also that we will need along the way case 1 occurs infinitely many times. That is, when you are going to consider these sums, these finite sums, and every time you have to know what the next nj is, you are going to see whether this sum is less than L or greater than L. So what this claim is, that it is saying that infinitely many times such sums are going to be less than L, and also infinitely many times they are going to be greater than or equal to L as well. What else do we need to prove? We need to prove that if we consider the sequence ANJ itself, you see, NJ is a sequence of natural numbers which helps us rearrange the terms of the series. The original terms in the series were AN, which themselves form a sequence of real numbers. Using NJ, we can rearrange the terms like this. So now you have a new sequence. That sequence also converges to 0. Why? We have to answer. Note from corollary 726 that this limit is 0. Where is this coming from? That is coming from the fact that our original series summation AN is given to be convergent, not absolutely convergent, but nonetheless ordinarily convergent, that is conditionally convergent. And we know that for any convergent series, the limit of its sequence of terms always is equal to 0. This is a necessary condition for convergence. That's what corollary 726 is. And using this itself, somehow we have to prove that this limit is 0. And using all these things, ultimately what you have to prove is that such finite series themselves converge to that real number L as j approaches infinity. And do you see what these finite series terms are? They are nothing but the terms in the sequence of partial sums of the rearranged series, that is this series ANJ. This is the rearranged series, right? We want to prove that this converges to L, which means proving that such terms converge to L, or rather, more specifically speaking, the sequence of such partial sums converges to L. So if we manage to show finally this, that proves the theorem. Okay, now before we abandon this for now, let us for once go back to the definition of Nj and let's try to see why we defined Nj like that. Why suddenly such sums less than L, greater than or equal to L? What is the reason for choosing that definition in the first place? So what is it? Say you have all the n i's defined for you, or all I less than j. So case 1 was this: if ANI, where I varies like this, is less than L, then we define Nj to be the minimum of this set. Now let me write this set not like how we have it in the proof, but like this. Whereas in case 2, we have our Nj defined like this. Do you see what is going on here in this definition? What is it that we have to prove ultimately in this theorem? That this series converges to L. So what are going to be the terms in the sequence of partial sums of this series? These terms. This is the sequence of partial sums. Now, if you have, say you are, this is a process, right? A recursive process. You have n0. You know what n0 is, and you look at a n0. So that is the term that you will get when you take j equal to 1. Okay. So you take j equal to 1, you see the previous term in your sequence, that is n0, you don't know what n1 is or what n1 should be. So this sum is equal to a n naught when j is equal to 1. It may be less than L or it may be greater than or equal to L. If it is less than L, what should be your natural next step? That means whatever you have here has fallen short of becoming L. So naturally you would want to add something positive or non-negative. You would not want to add something negative to it. That would decrease the thing further. So that's why we are choosing our n1 from a1, because we know that when we choose the suffixes from a1, then the a terms, that is those real numbers, are greater than or equal to 0. That helps us to reach L. Otherwise we would get even further away from L. So we choose a1. That means we choose n1 from a1, but which n1? Because a1 is infinite, but we want a definite n1 for the sake of uniqueness and for the sake of well-definedness. So we decide to choose the minimum value. Okay. In other words, what I am saying here is that n1 is the minimum of a plus minus n0 if this is the case. But if the opposite happens, if say in the beginning itself you have exceeded L, but still you want to continue the process, then you would want to take the next step in such a way that it reduces things. So that's why you choose n1 in this case from a minus, because we know that for the suffixes chosen from a minus, the corresponding a values are negative. So when you choose the n1 from here, and for the sake of definiteness you choose it to be the minimum value, then you have n1 in this case to be just this. It is the minimum of a minus minus n0. So you get the next term in the sequence of partial sums. What is that next term? That next term is actually nothing but this. an0 plus an1. That's it. That's what it is. Now your j value is 2, and now you want to see, okay, now I have got something new. Now what? Is this less than L or greater than or equal to L? If it is less than L, that means you want more. You want more non-negative terms. So n2 has to be chosen from here. But if it exceeds L, then you want a negative term. So this way, at every step you do the adjustment, And it turns out that if one continues like this without any end, because this is a recursive sequence, so infinitely many terms have to be chosen, then the resulting series actually converges to L. And the fact that the original sums this and this are divergent, that fact helps us to make sure that yes, this can be done. Okay, so in the next week on Sunday, we are going to see why is it that these things are true. But the you can already see that if we proceed like this and we manage to show all these claims, then we have the proof. That's it. So let me end the things here itself for tonight, and the next upload is this coming Tuesday. Oh, what is it that we did? What was the last thing that we did? Oh, we have already gone through graph theory once more. No? So this coming Tuesday, let us go back to group theory, where we are now going to start a new section, namely the section that deals with the relation of conjugacy on groups. It's an equivalence relation. We are going to see what the equivalence classes are, and then we will derive something called the class equation of a group, and then we will see there are many consequences of the class equation for finite groups specifically. So we will see that on this coming Tuesday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.